Today I'm speaking with Charlotte Deane, Head of the Department of Statistics at the University of Oxford and Professor of Structural Bioinformatics. Charlotte, thank you for coming in.
Thank you.
You're the head of a research group at Oxford, and your research group is the Protein Informatics group.
Yep.
What exactly is protein informatics?
So the idea behind protein informatics is proteins are the tiny molecules in your body that do things. And what we do is study them in a computational way. And primarily we're interested in the structures of these molecules, and we're also interested in how they interact with one another. So trying to use computational techniques based on mathematics and statistics to understand how those molecules work.
And how did you get into what you do now?
So I had a slightly peculiar path to what I do now. So I started off actually as an undergraduate in chemistry. And I always thought that's what I was interested in, and I was interested in how, small things worked, and I actually liked the very mathematical parts of chemistry, so quantum and all those kinds of things. And then this is probably the bit you shouldn't admit. I played a lot of sport at university, and in my degree, the fourth year, you had to do a year-long research project. But at that point, I was captaining the university hockey team. And so I was very concerned that whoever was going to be my supervisor for my fourth-year project would cope with me wanting to do this. And so I went around visiting people, talking to them about this. And I met a man called Graham Richards. And he said to me straight away, "Oh, my son plays university hockey. It would be fantastic if you joined the group." And so that's actually how I ended up doing this, because it was his area of research. And up until that point, I would never have guessed this would have been interesting. So it was an entirely accidental fall into doing this kind of work from that kind of interest. And from that, I learned how to think about protein structures and how to think about them as biological molecules, something I hadn't really thought about. So then I moved on and worked in Cambridge to actually do this in sort of an informal setting. And from there, my interest grew and grew and grew.
Let's dive into proteins in a small amount more detail, at least as much as I can get my hands around. Why is it that reconstructing the structure of a protein is a really difficult problem?
So there are two main reasons why it's really difficult. The first reason that it's really difficult is because they're actually, though they're tiny, they're made up of lots and lots of small components. So there's lots and lots of tiny things. So if you were just to randomly sample everything that happened to a protein to try and find the correct structure or shape it should be in, it would take you an enormously long time. There's actually something called Leventhal's paradox. He wrote it down in 1969, where he worked out that even if you sampled all the conformations at kind of the speed of 1 every 10 to 13, so incredibly rapidly, so in picoseconds, there's no way you would ever find the shape of a protein in the lifetime of a universe. So you've got this enormous space to search, is the first problem. The second problem is, once again, because they're made up of all these tiny components that go together, each one of these have sort of very precise interactions with one another. So there's the energetics of them interacting. So what you've got to fold up a protein is a sum of lots of tiny numbers. And of course, if you estimate any of those numbers incorrectly, the overall sum will be wrong. But because there's lots and lots of them, it's very likely you're going to estimate some of them wrong. So you're trying to explore a space that's incredibly complicated, and you're trying to explore it with a function that's very imprecise. So the chances of getting it right are very low. So you have to think of ways of getting round those two problems to be able to work out the structure of a protein.
And tell me about why it's an important problem to solve.
So proteins are the molecules in your body that do everything. So they're the ones that do stuff. So if you're thinking about moving your hands, there's a tiny proteins that make up your muscles are called myosin. And those are actually, it's those proteins contracting or expanding that allow your muscles to move. Or if you think about breaking down the food in your stomach, there's enzymes that do that. Those are proteins. The things that allow you to see, those are proteins. So everything that's doing something in your body pretty much is a protein. So we need to understand them for, you can think of just the general reason of wanting to understand how the whole kind of system of life works. But also if you want to think about something more practical like drugs, if you want to target a disease or help someone recover, the molecules you need to understand are the proteins that are either damaged in some way or over-functioning or under-functioning, and it's those you need to move or manipulate to make someone better.
That sounds like it has a huge variety of very definite implications. Do you partner with industry in order to make progress towards those implications?
So I'm very fortunate. So I ended up working with quite a lot of pharmaceutical companies. So I'd say about half the research we do in my group is alongside pharmaceutical companies. So we work with them on lots of different problems about understanding how you might predict the structure of a protein, understanding how you might target a specific protein in the body as opposed to any others, and even in some cases understanding how you might use a protein itself as a drug, so give someone an extra amount of a protein in order to improve them. And it's quite exciting and interesting to do that kind of work, because you get these very practical problems from a set of people who see the world slightly differently from my academic perspective, because they have very defined goals about what they want to achieve. But they have access to data and technologies that maybe I don't inside the university. So I find that interface really interesting. And we're very lucky, because the way I've been allowed to work with industry is something called open innovation. So they've allowed us to do all of this work and to be able to publish all of our computational results on this. Now, obviously, they then take these programs in-house and do other things with them, which are specific for their development of a specific drug. But it's been a really fruitful collaboration for us, not just in terms of development of drugs, but also, I think, in terms of greater understanding the system we work on.
If you can, in a kind of simple way, tell me about the approaches that people have taken in order to try and reconstruct protein structures, and then how your approach has differed from theirs.
Okay, so I guess the most protein structure prediction these days is done by something which is called homology modelling. What that really means is if you take a protein structure and you have another one which has a very similar set of chemicals in it, so it's similar, you can say that it will look very much the same. So it's almost like copying. So it's a bit like saying if you had the instructions for one car, you could make another car. But what you couldn't guess is the precise features of that car. So you would know it was a car, but say you wouldn't know what colour it was or exactly how big its wheels were. You'd know it looks roughly like this. And that's very much how homology modelling works. It gives you that kind of matching. So that's how most modelling is done. And we do some of that for what we would call our simple case studies. So we do a lot of that with antibodies, which are one of the proteins in your body, where we've got lots of structural examples, so we can use homology modelling as a starting point. The other type of modelling is where you have a list of chemicals that make up the protein that looks like nothing else you've ever seen before. And of course, this is where everyone gets excited, because it's much more interesting. And when people first started trying to model these, what they did was they used physics. They said, this is a physics problem, because, the energetics of this, all you're trying to do is fold this up. But because of the problems I've already mentioned, it turned out this was incredibly difficult. And there is now some success in folding it with physical functions. So it's actually a company in America run by Deane, where they've used very, very large supercomputers to try and solve the protein folding problem. And they've had some success with small proteins. The more common technique is you use a kind of statistical method for solving it, which is the kinds of techniques that we use. So here you basically kind of treat the protein like it's a jigsaw, and you take pieces from other known protein structures and you pretend they're the right shape for this piece, and then that bit for this piece, and that bit for this piece, and it just builds up a structure. And then you use a Monte Carlo usually to decide whether these pieces are good or bad against your energy function. And you just keep doing this repeatedly, and you build thousands and thousands of these things, and then you pick one out that you think is your best structure. What we do that's very different from that kind of standardized technique is that proteins are actually produced in your body. And it sounds fairly obvious, you must be making them all the time. But the way they're produced isn't that they magically all appear at once. The chemicals of the protein appear one by one. They come out of something called the ribosome. So you can imagine if my hand was the ribosome, the protein's just kind of popping out along like this. So the way that we do this is we acknowledge that in biology a protein is being produced, so we try and fold it as it's produced. And of course, what that has two advantages. One is potentially it's biologically more relevant, so it behaves more like the real system. But two, thinking mathematically, it's a simpler optimization problem, because now I only have to fold a small piece at a time, so I only have to deal with these, and I don't have to deal with the whole thing all at once, trying to fold it all at once. So it simplifies the energy landscape, it simplifies the concept of the number of moves I have to make, and so speeds up the entire process of trying to do this, and is potentially much more biologically relevant as well.
Out of the end of this analysis, you end up with a structure, a proposed structure.
Yeah.
How do you then know whether you've got it right?
So there are a few ways that you can do this. So there's always this thing, we kind of call it post-diction, which is where you pretend you don't know the structures of some proteins that people have already experimentally solved. So there's about 100,000 protein structures that have been solved experimentally now, which is a large number. It's not very large when I tell you that of the different proteins in your body, we know the structures of maybe about 10%. So it's not really got great coverage of humans in this sense. But you can pretend you don't know the structures of these things and then use your algorithms to predict them. But I'm trying to think, about maybe 15 years ago, a guy called John Moult in America set up something called CASP, which is the Comparative Assessment of Structure Prediction. And he actually turned it into a real blind testing setup. So experimentalists would tell us the sequences they were trying to experimentally determine the structures of, and that is a long, slow business. So there's months of work in doing that. So they tell us these sequences. We would all try and predict them. So groups from all over the world would try and predict them, and then you could look at your predictions at the end versus these answers and see how well you're doing. I should say the first thing that revealed was we were nowhere near as good as we thought we were, because it turned this real blind prediction was somehow harder. And I don't think anyone was cheating before, but it made it much more realistic. And so that's been a very interesting process of learning how to do it against this these blind test cases. Now, they're small in number because it's a difficult process, but it helps us refine our algorithms.
There's been a lot in the press recently about machine learning, artificial intelligence, of course, DeepMind and AlphaGo. Do any of those techniques have relevance to your science?
They do quite in some of the things that we do. So it's turned out that those techniques are quite good at predicting something which is called the secondary structure of a protein. So I've been talking all the time about folding the protein up into its complete kind of three-dimensional shape. A long time ago, people worked out there were some repeated elements that happened within that shape. These are called alpha helices and beta strands. And it turns out that machine learning techniques are very good at predicting where those will be. So they're incredibly good at that. People are starting to explore these techniques as ways of also trying to do the three-dimensional structure of the protein. But at the moment, nobody's successfully managed to make that transition to make them useful there. But I think it is something that's coming, that they will become part of the way we perform that search of the search space that we have to get around.
Your group has also gone as far as developing bits of software and providing services that you are not just using for your own benefit in terms of publishing papers, but you've made those freely available. Could you tell me a little bit about what are effectively software projects that are kind of embedded within your group?
Yeah, so this was something that I wanted to do from right when I started. So when I sort of started doing this kind of research, I would read other people's research papers and they would say there was a program that did X. But it turned out getting the program that did X was very difficult. And even when I did get it, it wasn't in a state that was very easy for me to use. And having experienced that frustration, I kind of had this underlying feeling that if I ever got to the stage where I had a group and I had the kind of ability to do this, I would try and ensure that what we did was develop software not to a kind of, it sounds a bit an academic standard, but develop it so that people could just take it out and use it and build from it. After all, that's kind of what I'm trying to achieve. So we set about working out how to embed within our group some software engineering principles as part of what we did. So to have things like version control as a normal part of our process. I should admit this doesn't always work. I mean, we are an academic research group made up of students and postdocs. So it's, sometimes hit and miss. But we're very keen to develop software to a level where people will be able to take these programs out. And it goes alongside that idea of open innovation that I talked about with the pharmaceutical companies, that what we're trying to do is develop these as services. So if you go to our website, not only can you download our programs, but you can also just use them interactively if you want. And that's more for biologists. So biologists are unlikely to want to kind of type into a command line screen to try and work out how to make something happen. But if you can make it very simple for them, say, to enter this list of chemicals that make up the protein they're interested in, and then what they get is an image and a picture or a rotatable thing that they can look at to see that protein, you've probably given them a lot more interest in what you're trying to achieve.
It's interesting that you mentioned visualization there. With these hugely complicated structures, visualization must be quite a challenge in representing the information that you want to get across in that way. How do you go about doing that? So, very lucky kind of in the protein field that there's been a lot of people who've done a lot of work over a long period of time about developing visualization software. So there's lots of pieces of freely available software that people have spent
a very long time developing that are very good at doing the visualization. One of the key things we've learned is to pick, we use a particular package, but to pick it because it allows us to we can actually write a kind of software interface to it, so we can affect what is being coloured in what way and other things that can happen. The other part of visualization we've done, which is represented by these models here. So we've started to be able to build three-dimensional models of the protein. So these are printed on a 3D printer. And this was quite cool because we could use it actually as a learning tool for students. So it's much, much more interesting to see a protein not on a screen, but to be able to hold it in your hands. But for them to also see how you go through the process of taking it from a set of coordinates to something that can be printed is also, for them, an interesting software challenge and a development of their understanding of how it works.
Let me ask you to look forward a little bit about what your research might be based around in maybe 10 years' time. Do you have a feeling of the direction that you're heading in?
I think in some areas, yes, in others, no. So a lot of the work I do with pharmaceutical companies is concentrated around antibodies. So they're the kind of natural defenders in your system, but they're also used by drug companies as basically as drugs. And I think that work is going to kind of mature to the stage where computational prediction will be something that can just be done and be very, very useful within it. And it will be much more complicated designs of proteins that become interesting. And I think it is the same thing that's going to happen on the other side of the work in terms of protein folding. I hope, I don't know if it will be me, but I hope within my lifetime somebody really does solve the problem of how, given this string of chemicals that make up a protein, what its three-dimensional structure will be. We can't do that at the moment. We can do it sometimes, but we're getting better and better understanding of that. But I think it's going to be the next stage on, which is going to be very exciting, which is, can you computationally design these proteins? So could I write down a string of letters that made a protein that did something very specific? So stepping from the natural system one stage on. And I should say there are a lot of people who already work in that area and that problem, and you can kind of see that that's where the field would become very exciting in terms of different things you'd be able to do and really have an understanding of the biological system. And I suppose the other thing that I find very exciting is at the moment, I'm kind of talking about each individual protein in some way. But obviously in your body, when they're doing things, they're all interacting with one another. So understanding these much larger scale complexes of how 10, 20, 30, 40 proteins interact with one another and work as what are called molecular machines to make something happen. Or even something as simple as how do the proteins within your heart, can you go all the way from understanding the proteins in your heart to the fact that your heart beats? Which now we can kind of hand wave do, but it would be brilliant to have that complete description all the way out to understand the whole thing.
Charlotte, it's been fascinating talking to you. Thank you very much for coming in.
Thank you.